How was our universe created? What does it look like beyond our solar system? Does our universe hide many other inhabited worlds like our own? How can we explain the mysterious forces observed in the cosmos, such as the immense black holes that absorb everything in their vicinity, even light? The James Webb Space Telescope was designed to answer these and many other questions. This jewel of space technology was developed by NASA with the participation of the European Space Agency and the Canadian Space Agency. The James Webb Space Telescope was designed to continue Hubble's work, but better. It carries cutting-edge instruments that enable it to see at longer wavelengths, notably in the near, mid, and far infrared. When it was launched on December 25, 2021, James Webb was the largest and most expensive space telescope ever developed. It took more than 25 years to build, and the scientific community now has high hopes for this telescope, which should help us in the coming years to solve the great unsolved mysteries of modern astronomy and trace the complete history of our universe. After its launch, it took a year to break it in, calibrate it, and learn how to use it to its full potential. The James Webb still has many years ahead of it, as its mission is expected to last 20 years. The first images unveiled by the telescope from July 2022 have not disappointed scientists' hopes and have impressed the general public with their sharpness, detail, and color. One of the James Webb's primary objectives is to discover the elements essential for life elsewhere than on Earth, in particular on exoplanets orbiting a star, similar to our Sun. But that's not all. The Space Telescope's mission is also to discover the origin of black holes and to probe the universe's past further back in time than any other telescope has yet done. The James Webb should be able to detect the very first galaxies, those born just after the Big Bang, and explore the space-time between these distant galaxies and our solar system in order to reconstruct the entire history of our universe. Since its launch 2 years ago, the James Webb has continued to surprise astronomers with astonishing discoveries. Its observations have even begun to call into question some astrophysical models, notably those concerning the youth of the cosmos. Indeed, according to observations made thanks to the James Webb, it would seem that everything, the first black holes, the first galaxies, arrived earlier and faster than scientists had previously predicted. Dear traveler, welcome. Today we're off to explore some of the telescope's latest images and the new questions they may have raised for the scientific community. But before we set off on a new adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and fasten your seatbelts. It's going to be an intense journey, rich in discoveries. Here's an image of the so-called Pillars of Creation in the Eagle Nebula, or NGC 6611. These columns of interstellar dust are in fact a star-forming zone at the heart of one of the most productive star-forming zones in the Milky Way. This photo dates back to 1995. It was taken by the Hubble Space Telescope, the predecessor of the James Webb, which was launched in 1990. Now take a look at this photo, taken in October 2022 by the NIRCam infrared camera of the James Webb Telescope. The difference is striking. It's like putting on glasses for the first time. A second image was taken by the James Webb's MIRI instrument, the only one that can see in the mid-infrared. This image is darker, and the stars can't be seen as clearly as in the first image, but it's still very impressive. It's the infrared vision of James Webb's instruments that allow us to see through the clouds of gas and dust and distinguish all these stars. The image is so detailed that it's easy to interpret. You can clearly see red dots representing baby stars, only a few 100,000 years old, and red streaks in the clouds of dust and gas that are actually nascent balls of gas that will later become stars. There's no shortage of examples of images that have been recaptured by the James Webb with greater sharpness and precision than those taken by Hubble. Why? Because the James Webb, unlike Hubble, observes the universe in the infrared. This enables it to capture the rays of the first stars, which were emitted in ultraviolet form, but whose wavelengths, stretched by the expansion of the universe, then shifted towards the red. The more pronounced the red shift, the more distant and ancient the star. Between May and September 2023 alone, the James Webb produced an impressive number of images of stunning sharpness and detail. Colliding or merging galaxies, stellar nurseries, gigantic black holes, magnificent nebulae. The Space Telescope lets us see what we can never see with the naked eye, not only because it's too far away, but also because our eyes can't see in these wavelengths. These images will undoubtedly help us to better understand the genesis of the universe, but also to advance our search for extraterrestrial life, somewhere in the universe beyond our solar system. For the first time, the James Webb is fully capable of analyzing the atmosphere of an exoplanet. A huge step forward, given that the composition of an exoplanet's atmosphere can give us important clues about its chances of harboring any form of life. For a planet to be potentially habitable, it needs to bring together a number of ingredients, none other than those required for the development and maintenance of life forms. On Earth, life has been able to develop thanks to liquid water, a source of energy in elements such as carbon dioxide, hydrogen, and oxygen. For an exoplanet to be habitable, it must therefore be located at a certain distance from its star, so that temperatures remain moderate and allow water to be maintained in liquid form. But it must also have the right chemical elements, a source of energy, such as volcanic activity, and an atmosphere to protect living organisms from the dangerous radiation emitted by its star. Of the more than 5,500 exoplanets discovered to date, researchers are nurturing the hope of one day finding one that meets the necessary conditions and on which a form of life could be discovered. You're about to find out how the James Webb Space Telescope can help us in this quest. To analyze the atmosphere of an exoplanet, we wait for it to pass in front of its star. This is called a transit. In this way, we can receive the light from the star that has passed through the planet's atmosphere. Thanks to this method, the James Webb's instruments will be able to identify the planet's chemical composition. The James Webb has two types of instrument: cameras to take images and spectrometers to observe light spectra. While the general public is most fascinated by the images taken by the telescope, it's the spectrometers that are of most interest to scientists. Here's how a spectrometer works. Light passes through a lens, much like a film camera. This lens concentrates all the light in a single point, so that it can then pass through a narrow slit. The light then passes through a second lens and a prism, which breaks the light down into a number of colors like a rainbow. We can then distinguish the colors that make up the light. The light spectrum is a treasure trove of information. A light spectrum is distinguished by the black lines through which molecules reveal their identity by absorbing light. This is because molecules in space will absorb certain wavelengths of light. Each molecule has its own signature. Nitrogen, hydrogen, or sodium do not have the same spectrum. By analyzing these black lines, we can identify the signature of calcium, nitrogen, or hydrogen. It's as if the molecules left their fingerprints on the light spectrum. The James Webb spectrometers have been specially designed to detect the fingerprints of molecules in the infrared part of the light spectrum. The molecules of interest in our search for extraterrestrial life are those associated with life: carbon monoxide, carbon dioxide, hydrogen, and methane. Among James Webb's notable contributions is his study of Wasp 39b, an exoplanet located 700 light-years from Earth, in the Virgo constellation. Wasp 39b is a gas giant slightly larger than Jupiter. However, it is much less dense than Jupiter, which facilitates observations. In fact, its atmosphere is puffier and more extensive, making it easier to detect the molecules that make it up. Hubble had already studied Wasp 39b and detected water vapor in its atmosphere. James Webb's more detailed instruments have enabled us to find out more. In Wasp 39b's atmosphere, scientists detected a molecule essential to life: carbon dioxide, or CO2. On Earth, CO2 is produced naturally through geological processes and is vital for plant growth. James Webb also detected sulfur dioxide in Wasp 39b's atmosphere, the first time this molecule has been detected on a planet outside the solar system. Once again, this discovery marks a turning point, since sulfur dioxide, present in our ozone layer, plays a crucial role in absorbing part of the sun's UV radiation, which is harmful to the Earth and to us. However, Wasp 39b lacks some important elements to make it a candidate for life as we know it. Firstly, a solid surface. For this planet is a gas giant, and not like Earth, a rocky planet. The results are still uncertain. It may have no atmosphere, but it may have a very thin one. The second missing element is a moderate temperature that would allow water to remain in liquid form. On Wasp 39b, the temperature is over 870 degrees Celsius, or 1600 degrees Fahrenheit. The exoplanet is even closer to its star than Mercury is to the Sun. Although Wasp 39b is clearly not habitable, the observations made by James Webb are still very useful and exciting for researchers. Above all, they provide a better understanding of the chemistry of exoplanet atmospheres. Astronomers hope to be able to establish models for the formation and evolution of exoplanets by better understanding their atmospheric evolution. In the case of Wasp 39b, scientists believe it was formed by the collision of small rocky bodies, which merged to form an exoplanet. The exoplanet then moved closer to its star as it evolved. To provide such precise data, the telescope had to be calibrated over a long period of time. After its launch on December 25, 2021, the James Webb took a month to reach its L2 orbit point, located around the Lagrange point, 1.5 million kilometers, or 930,000 miles from Earth, on the opposite side of the Sun. Once in orbit, a further 5 months of calibration were required, meaning that the first images taken by the telescope were not released until July 2022. It was particularly important to ensure that the James Webb was working properly before launch. Adjustments had been made to Hubble to correct faults that were only detected after it had been put into orbit via a mission by the U.S. Space Shuttle Endeavour in 1993. But in the case of James Webb, post-launch corrections were unthinkable, given that the telescope orbits 1.5 million kilometers from Earth. Fortunately, no anomalies were reported when the telescope went into operation in early 2022. The launch performed by Ariane 5 was perfectly executed, which means that the telescope still has fuel reserves for 26 years, far more than the 5 to 10 years originally hoped for. Teams monitoring the telescope are taking great care to ensure that no micrometeorites hit its mirror, or any other accident that would bring the James Webb mission to an early end. Calibration of the James Webb took several months. This step is very important to ensure the reliability of the telescope's discoveries, in particular, the age of early galaxies. If the data are not reliable, this will have an impact on the veracity of our knowledge of our universe. To calibrate the space telescope, a team used the globular cluster Messier 92 as a reference. As one of the brightest and oldest groups of stars, it has been widely observed, and a wealth of reliable data is available. This team of researchers therefore compared the data returned by the James Webb with what was already available, and adjusted the instruments and sensors accordingly. No easy task, since the James Webb has no fewer than 18 sensors. Once the calibration had been fine-tuned, the scientists were able to start measuring the brightness of distant galaxies to deduce their distance with great precision. For the moment, the most distant galaxy, the first galaxy, has yet to be identified, but researchers are not giving up hope. Thanks to this calibration, the images we can see today are not only magnificent but also realistic. Or at any rate, researchers are working to make them as faithful as possible to what the telescope observed, while adapting the images to our human eye. The images you can see, such as the phantom spiral galaxy, NGC 628, the Crab Nebula, Jupiter and Neptune with its rings, have all been reworked. The very first image taken by the James Webb left a lasting impression. It was unveiled on July 11, 2022. In this image of the deep universe, we can see the galaxy cluster SMACS 0723, made up of thousands of galaxies, and celestial objects of very low brightness. But this image was not broadcast as it was taken. It was produced by compiling images taken by the James Webb at different wavelengths over a period of 12.5 hours. The result is the sharpest infrared view of the distant universe ever obtained with a telescope. How are images taken by the James Webb reworked? The human eye can only see a very narrow part of the light spectrum, from violet to red, i.e. the colors of the rainbow. But the light spectrum is much broader than that, with light on both sides of the spectrum. The James Webb focuses on the infrared, so it can see farther than the human eye on the red side of the light spectrum. These are the data imaging developers who rework the images taken by the James Webb's near and mid-infrared instruments. In addition to computer skills, this job requires an artistic flair. It involves transposing infrared light into colors that our eyes can distinguish, i.e., one of the colors of the famous rainbow. The James Webb takes several successive images of the same celestial object with different infrared filters at different distances. The different wavelengths, i.e. near, mid, and far infrared, are then converted into the colors of the rainbow, according to the rules of data colorization, known as chromatic order. The principle is simple. Data is captured in the infrared, then shifted to the visible part of the spectrum. The principle is the same as transposing a song played on the piano into a different key. The melody remains the same. Thus, the farthest wavelength will be red, the middle wavelength green, and the closest blue. The filters are superimposed to create a colorized image. This image remains fairly flat, so it needs to be reworked one last time. It's this last stage that most calls on the developer's subjectivity and artistic sense. The idea is to obtain an image that is beautiful to look at without removing or adding elements, while remaining as faithful as possible to reality. We're now going to take a look at the latest images taken by the James Webb Telescope, which have enabled researchers to advance a little further in their quest for knowledge about our universe. Let's begin our exploration with a discovery that is one step closer to finding a habitable world beyond our solar system. On September 12, 2023, NASA reported that the James Webb had found gas showing the presence of an ocean on a planet 120 light-years from Earth, the planet K2-18b. The telescope found traces of molecules such as carbon, methane, and carbon dioxide, which could indicate that this exoplanet is covered by an ocean with a hydrogen-rich atmosphere. K2-18b would therefore be a high-oceanic planet, i.e. an ocean planet with a predominantly hydrogen atmosphere. In fact, Hubble had already found traces of water vapor in this planet's atmosphere, but the James Webb observations once again confirm scientists' suspicions. The James Webb also discovered a molecule called dimethyl sulfide, or DMS. This molecule is only produced on Earth by life, notably phytoplankton. On K2-18b, there may therefore be the equivalent of terrestrial phytoplankton. This discovery is therefore very promising and could be a clue to life on a planet in the near universe. All the more so as K2-18b is located in its star's habitable zone. NASA remains cautious and has made it clear that further checks are required to confirm the presence of an ocean on this planet. In any case, the information gathered by the James Webb is best interpreted by this hypothesis of an ocean on the planet's surface. The most widely accepted hypothesis at present is that, like Neptune, K2-18b harbors a vast high-pressure ice mantle with a surface ocean and a thinner, hydrogen-rich atmosphere. The ocean, however, would be too hot to be liquid or habitable. Confirming this hypothesis will be complicated, even with the prowess of the James Webb. Indeed, the brightness of this exoplanet's parent star is so low that when the planet transits in front of it, only a tiny fraction of the light reaches the telescope. However, just 2 observations have yielded a wealth of interesting data, and further observations are in progress. So it's a safe bet that we'll soon have new information about this planet. On the other hand, some scientists remain skeptical about the concept of a high oceanic planet. Admittedly, models and simulations show us that they could very well exist. But the existence of water in liquid form is subject to very precise parameters with very small windows, and all it takes is for one of them to move just a little for water to no longer exist in liquid form. For example, a certain level of hydrogen in the atmosphere of an exoplanet can guarantee water in liquid form on its surface, but if there's just a little too much hydrogen in the atmosphere, the water no longer exists in liquid form, but in supercritical form. Or, as on Earth, mechanisms would have to exist to stabilize the conditions that make it possible for water to exist in its liquid state. However, it is unlikely that all oceanic planets possess the same plate tectonics and volcanism mechanisms as Earth. All we can do now is wait for further data from James Webb to find out more about this exoplanet and about oceanic planets in general. Let's move on to another James Webb discovery. Take a look at this image. It was taken by the James Webb on August 31, 2023. You can see Supernova 1987A, or SN 1987A, one of the best-known supernovae. Located 168,000 light-years away in the Large Magellanic Cloud, it has been observed for almost 40 years. Why, if it's already known, has this supernova been observed again with the James Webb? What did astronomers expect to discover? Quite simply, because astronomers hope to use it to understand how a supernova develops over time. To better understand James Webb's recent discoveries, let's take a look back at the story of this supernova's discovery. As its name suggests, SN 1987A was discovered in 1987, in the month of February. The discovery was made by Chilean astronomers Ian Shelton and Oscar Duhalde. It is a Type II supernova, i.e. the result of the gravitational collapse of a massive stellar core that has exhausted its nuclear fuel. Let's keep it simple. Originally, there was a star called Sandalik 69202, a blue supergiant born 10 million years ago from a stellar collision with fusion. This star had a mass 20 times that of our Sun. When the star ran out of fuel, it was unable to maintain a balance between the gravitational forces and the pressure forces generated by nuclear fusion. Eventually, it exploded, releasing a large amount of light and matter into space, resulting in a Type II supernova. SN 1987A was the first supernova to be observed with the naked eye since the dawn of modern astronomy. Since its discovery, telescopes around the world have observed this supernova, including NASA's Chandra X-ray Observatory, which has examined it repeatedly during 17 years of scientific operations. Between 1999 and 2013, Chandra's data showed an expanding ring of X-ray emission that grew brighter and brighter, certainly produced by the shock wave from the supernova's explosion. Hubble had also observed this supernova, so it made sense to continue observations with James Webb. The photograph taken by the James Webb Telescope has enabled scientists to advance their understanding of this supernova. At the center of the supernova, you can see a keyhole formed by the matter ejected from the supernova, namely gas and dust, a structure that has never been observed before. To the left and right of this keyhole structure, you can also see crescents, shapes recently discovered by the James Webb. Beyond the center of the supernova, you can see an equatorial ring of material ejected tens of thousands of years before the supernova exploded. This equatorial ring contains bright hot spots that formed when the shock wave from the explosion caught up and heated the material in the ring. Around the equatorial ring, you can make out two faint outer rings, which according to researchers are the result of the interaction between the star's stellar wind emitted before the supernova and the matter previously ejected by the star. Unfortunately, the dust at the center of the supernova is so dense that not even the near-infrared light detected by the James Webb can penetrate it. That's why the keyhole is so dark in the photo. The telescope, although very advanced, was therefore unable to detect the supernova's residual star. Yet this is what scientists had hoped to observe. In fact, the collapse of a star's core, as happened with SN 1987A, usually leads to the formation of a neutron star or a black hole. In the case of this particular supernova, it would be a neutron star. Astronomers hope to be able to observe this neutron star once the gas and dust in the supernova's inner region have dissipated slightly. James Webb's next discovery we're going to talk about concerns Herbig-Haro objects, abbreviated as HH. Herbig-Haro objects are luminous regions surrounding newborn stars. When stellar winds or jets of gas spewed out by newly born stars create shock waves, and these shock waves collide at high speed with nearby gas and dust, Herbig-Haro objects are formed. On September 14, 2023, an image of the object Herbig-Haro 211, or HH211, was released. Located in the Perseus constellation, around 1,000 light-years from Earth, HH211 is a protostar that looks very much like our Sun when it was only a few tens of thousands of years old. Its mass is currently only 8% that of our Sun. HH211 had already been observed from the ground, but this is the first time we've been able to see it in such detail. The James Webb Telescope also photographed HH 797, an object located in the immediate vicinity of star cluster IC 348, at the edge of the Perseus molecular cloud, around 600 light-years from Earth. Observing this object from the ground, astronomers had noted that the cold molecular gas associated with HH 797 had a double motion. To the south, there was a redshift, meaning that the region was moving away from us. To the north, there was a blue shift, indicating that the region was moving towards us. Thanks to James Webb's observations, astronomers were able to distinguish two parallel jets instead of one, each with its own speed and history. This could mean that HH 797 is around a double star, and not, as astronomers have long assumed, a single star. Herbig-Haro objects are fascinating phenomena. The speed of the stellar winds and gas jets released by newly born stars is dizzying, and the shock waves created by the collision between these energies and the surrounding gas and dust are impressively powerful. These objects show us that within a star-forming zone, there are intense dynamics and energy flows that are both complex and incredible. With its infrared instruments like the NIRCam, the James Webb is perfectly equipped to observe newborn stars and Herbig-Haro objects, and thus better understand the dynamics at work during star formation. Let's continue our exploration of recent discoveries by the James Webb Telescope. On October 10, 2023, the James Webb observed the brightest star-forming region of the Small Magellanic Cloud, NGC 346. The Small Magellanic Cloud, also known as SMC or NGC 292, is a satellite galaxy of the Milky Way, and thus part of the local group, our group of galaxies. This irregular dwarf galaxy is visible to the naked eye in the southern constellation Toucan. It's one of the most distant objects visible to the naked eye, located some 199,000 light-years from Earth. In fact, you can only see it from the southern hemisphere, in a place far from pollution. The Small Magellanic Cloud should not be confused with the Large Magellanic Cloud, with which it forms a pair. The two are linked by the so-called Magellanic Bridge, a bridge of gas and stars. It's the Small Magellanic Cloud that interests us here, as it was in this galaxy that the James Webb was able to observe NGC 346, a particularly bright star-forming region. This image of NGC 346 was taken by James Webb's MIRI instrument. NGC 346 is a region in which stars are regularly born. It has already been photographed by Hubble, so this is not the first time it has been observed by astronomers. However, the near-infrared images taken by James Webb in January, followed by mid-infrared images in October, have enabled us to refine our knowledge of this region. The James Webb images show bands of gas and dust, dotted with luminous spots, filled with young protostars. Astronomers were astonished that the images revealed cold gas and dust emissions. The Small Magellanic Cloud is a more primitive galaxy than our own, so astronomers expected it to be fairly dust-poor. In fact, this neighboring galaxy contains fewer heavy elements than the Milky Way. Heavy elements are forged in stars by nuclear fusion and supernova explosions, so they appear late in a galaxy's lifespan. The Small Magellanic Cloud must contain heavy elements, since it is heavy elements such as silicon and oxygen that are responsible for the formation of galactic dust. The James Webb images show polycyclic aromatic hydrocarbons and dusty silicates, as well as dust heated by the most massive and brightest stars, shown in red in the photos. Bright spots and filaments can also be seen, concealing a large number of protostars. The researchers counted 1,001 red stars, most of them young stars masked by dust. The images of NGC 346 are important because they will give us a better understanding of the more primitive galaxies that existed billions of years ago, at a time called cosmic noon, when star formation was at its peak and heavy elements were present, but in lower concentrations than today. Here is an image of another star-forming region taken by the James Webb's NIRCam, which immediately struck the general public with its sharpness and detail. This is Sagittarius C, or SGR-C, a star nursery at the center of the Milky Way. This image has made an indelible impression on the general public, as well as on researchers, because until now, infrared data on this region had never been obtained with such a high level of sensitivity. Offering unprecedented detail, the image revealed many previously unobserved features of this region. According to the researchers, the center of the Milky Way is the most extreme environment in our galaxy. Sagittarius C is located very close to the center, just 300 light-years from our galaxy's supermassive black hole, Sagittarius A. This star-forming region is therefore quite far from us, at 25,000 light-years from Earth. In this image, we can see around 500,000 stars and clusters of protostars, i.e., stars in the process of forming, or if you like, baby stars, and all in a volume about 50 light-years across. One of these protostars is particularly massive, with an estimated mass 30 times that of the Sun. This protostar blocks the light behind it, so James Webb was unable to see all the stars in Sagittarius C. This is a pity, as the area hidden by the massive protostar promises to be one of the densest. The darker areas visible in the image are also star nurseries. More precisely, they are Bok globules, i.e., dark clouds of dust and gas, in which the birth of stars can begin. But what most intrigues researchers is this region, shown in cyan blue, which extends over 25 light-years and is made up of ionized hydrogen. Typically, hydrogen is ionized by energetic photons emitted by massive young stars, but in this case, it's the sheer size of the area that has astronomers wondering. On top of this, researchers are puzzled by the needle-like structures seen in the photo, which appear to be oriented chaotically in several directions. These structures are astonishing, and for the moment, astronomers have no explanation. This is the first time such structures have been observed in the heart of the Milky Way. In any case, this highly detailed image confirms that the center of our galaxy is a tumultuous zone, boiling with energy. Clouds of magnetized gas form stars, which in turn emit stellar winds, jets, and radiation that impact on the surrounding gas and create impressive objects. An extreme environment that researchers are only just beginning to study. James Webb's detailed images will undoubtedly be a great help in the quest to understand star formation at the heart of our galaxy. Among James Webb's most significant discoveries at the end of 2023 was the discovery of a never-before-seen jet stream near the equator of Jupiter. This impressive discovery was made by comparing James Webb images with those from Hubble. It was subsequently published in the renowned journal Nature on October 19, 2023. It brought to light a feature of Jupiter that had never been seen before. According to NASA, it's a high-speed jet stream, moving at around 515 kilometers per hour, or 320 miles per hour, twice as fast as a Category 5 hurricane. In fact, it's a well-known phenomenon, even though it has never been observed on Jupiter before. A jet stream is a tube of strong winds located around 8 to 15 kilometers, or 9 miles in altitude, at the boundary between the troposphere and the stratosphere. The one detected by James Webb lies above Jupiter's equator, at around 40 kilometers or 25 miles above the clouds, and extends over 4,800 kilometers or 3,000 miles across. This discovery gives us our first glimpse of how the layers of Jupiter's atmosphere interact with each other. According to the researchers behind the study, published in the journal Nature, Jupiter has a complex pattern of winds and temperatures, and the jet stream that has been spotted could vary considerably over the next 2 to 4 years. It will be further studies by the James Webb that can help us determine whether the jet's speed and altitude tend to evolve over time. On July 27, 2022, the James Webb Telescope had already delivered unprecedented images of Jupiter. These were perfectly sharp, well-defined images, revealing details of the largest planet in our solar system. The James Webb images, taken with the NIRCam near-infrared camera, reveal Jupiter's rings, its smaller satellites, Amalthea and Adrastea, and above all its polar auroras, 100 times brighter than those seen on Earth. Jupiter's polar aurorae are caused by the encounter of matter thrown up from the moon Io with the gas giant's atmosphere. A study carried out in August 2021, using recordings from the Keck telescope in Hawaii, had shown that these aurorae acted like a radiator, providing heat to the whole planet. The James Webb images of Jupiter also show the famous red spot, which appears white because it reflects sunlight. Jupiter's Great Red Spot is a gigantic anticyclone in the planet's atmosphere, located at 22 degrees south latitude. Although it's not necessarily obvious from the James Webb images, this red spot is slightly larger than our planet itself. In 2015, its dimensions were estimated at around 15,000 kilometers, or 9,300 miles in length, and around 12,000 kilometers, or 7,500 miles in width. In the past, it would have been even larger, since it is estimated that over the course of the 20th century, it has shrunk by half. In this anticyclone, winds are said to blow at 700 kilometers per hour, or 430 miles per hour. The Great Red Spot was so named around 1878, but today it appears rather brown. James Webb did not discover this red spot, as it has been known for over 350 years, and very clear images of the phenomenon had already been obtained, notably by the Cassini-Huygens mission. However, these images will enable scientists to better study the interaction between the dynamics of Jupiter's atmosphere, chemical composition, and temperature in and above the Great Red Spot. Here are a number of images taken by James Webb and now well known to all astronomy enthusiasts. In this image, taken on July 12, 2022, you can see a young star-forming region in the Crab Nebula, 8,500 light-years from Earth. A region that had already been photographed by Hubble, but never with such precision. In this image, taken on September 12, 2022, you can see the Orion Nebula, the closest nebula to us at around 1,350 light-years from Earth. Once again, this region had already been photographed by Hubble, but James Webb's photo revealed new details. The image in front of you is very sharp. You can even make out Orion's bar, a wall of gas and dust inside the nebula, and two very bright stars that are part of the trapezium cluster. We can also see a cocoon of stars with a protoplanetary disk, conditions similar to those that led to the birth of our Sun and its planets 4.5 billion years ago. Another nebula was also photographed by James Webb on September 6, 2022, the Tarantula Nebula. Located 161,000 light-years from Earth in the dwarf-large Magellanic Cloud Galaxy, this nebula is the largest and brightest star-forming region in the entire group of galaxies not far from the Milky Way. This nebula is also home to the hottest and most massive stars known. For all these reasons, the Tarantula Nebula is of great interest to scientists. Here's a final image taken in 2022, on July 12th to be precise, by the James Webb. It shows the Southern Ring Planetary Nebula, located around 2,500 light-years from Earth, in the constellation of the Veils. James Webb's image enabled scientists to discover the origin of this planetary nebula, a binary system of dying stars. On October 30th, 2023, the James Webb unveiled a new nebula image, the Crab Nebula. Located 6,500 light-years away in the constellation Taurus, this nebula is in fact a supernova remnant. The Crab Nebula had already been photographed by Hubble in 2005, but here again, the details provided by the James Webb images have enabled scientists to better understand its origin. The James Webb data have enabled us to establish the composition of the ejected material, in particular, its iron and nickel content, which will tell us what type of explosion produced the Crab Nebula. By the way, take a look at the two images side by side, the Hubble image and the James Webb image. You can see that in the James Webb image, there's more detail in the central regions of the nebula, where you can see the emission of dust grains. The orange filaments you can see in the image taken by the James Webb are the remains of a star that has now disappeared. The supernova created by the explosion of this star was seen on the Asian continent in 1054. For 23 days, the supernova shone brightly and could even be seen in broad daylight. Even today, the nebula continues to expand at a speed of 1,500 kilometers per second, or 930 miles per hour, as a result of this explosion. In the center of the image, you can see a translucent zone of what is known as synchrotron radiation. Synchrotron radiation is generated by the presence of a pulsar, a neutron star that rotates very rapidly and emits strong radiation. Thanks to these breathtaking details, scientists hope to glean valuable information for a better understanding of a star's life cycle. The image before your eyes is considered one of the most complete views of the universe ever obtained. This image has been reconstructed using James Webb and Hubble images. It shows the MAX 0416 galaxy cluster, 4.3 billion light-years away. More precisely, MAX 0416 is a pair of colliding galaxy clusters which will eventually merge to form an even larger cluster. Researchers combined images taken in visible light by the Hubble telescope and in infrared by the James Webb Telescope to reconstruct this colorful view of our universe. In fact, why is this image so colorful? Quite simply, because it shows thousands of galaxies that appear differently colored according to the wavelength range in which they shine, i.e., from 0.4 to 5 microns. The nearest galaxies, regions of intense star formation, appear in blue and were detected by Hubble. The most distant galaxies, on the other hand, appear in red and were detected by James Webb, as they are too far away for Hubble to see. Objects colored green are located at mid-distance. James Webb didn't just take a picture of this cluster of galaxies at a given moment in time. He observed the region 4 times, a week apart, to identify what are known as transient objects. Transients are objects whose brightness varies over time. 14 transient objects were detected, 12 of which are likely to be single stars or multiple star systems, and 2 are likely to be supernovae. This means that transient phenomena could be much more numerous than previously thought. Among the transient phenomena identified in the MAX 0416 cluster, one in particular has caught the attention of scientists. This is a giant star that has been nicknamed Mothra because of its monstrous nature. It is located in a galaxy that existed some 3 billion years after the Big Bang and is amplified by a factor of at least 4,000 through gravitational lensing. Mothra was already visible in Hubble's observations almost 10 years ago, which is quite unusual. Indeed, it would take a very specific alignment between the galaxy cluster in the foreground and this star in the background for it to be so amplified. However, the mutual movements of the star and the cluster should have broken this alignment. The explanation put forward by the scientists is the presence of an additional object in the foreground group, which would add magnification, like a globular cluster. This object would have a mass between 10,000 and 1 million times that of our Sun. The MAX 0416 cluster has been nicknamed the Christmas tree cluster because, according to NASA researchers, it is very colorful with flickering lights, like the lights on the tinsel of a Christmas tree. Among the most recent images taken by the James Webb is this impressive photograph. This is no trick. This cosmic ghostly figure is a galaxy in formation called Aztec 71, more precisely, a dusty star-forming galaxy. This is a type of galaxy hitherto reputed to be very rare and almost invisible. Hubble had already attempted to photograph this galaxy in formation, but without any real success. Aztec 71 is very difficult to observe. This galaxy is the seat of star formation, but it's shrouded in a dusty veil that's very difficult to penetrate. That's why Hubble, which couldn't see in the infrared like James Webb, wasn't able to obtain satisfactory images. James Webb's image, broadcast on October 10, 2023, is very striking. It looks like a ghostly face. It looks like a tiny drop in the vastness of the universe. But this galaxy is actually forming hundreds of new stars every year. This discovery shows us that there could be a whole population of galaxies hiding from us that we won't be able to observe until we develop even more powerful instruments than the James Webb, capable of seeing in even more extreme wavelengths. This discovery has also led researchers to claim that this type of galaxy, thought to be extremely rare, is in fact 3 to 10 times more common than previously thought. Like the image you've just seen, this photo of the exoplanet Wasp 107b, taken by the James Webb, is also very impressive. Wasp 107b is a gas giant, orbiting a highly active K-type main sequence star, located around 200 light-years from Earth. It is nicknamed the Hot Super Neptune. One of its special features is that it is one of the exoplanets with the lowest known density. Its mass is only 12% that of Jupiter, while its diameter is comparable. This is due to the fact that its atmosphere is greatly expanded by the radioactive heating of its star, around which it orbits in just 6 days. Temperatures in its atmosphere reach hundreds of degrees. Wasp 107b's highly expanded atmosphere has earned it the nickname of Cotton Candy Planet. In any case, it facilitates measurements of the planet's atmospheric spectrum. Astronomers had already discovered helium in its atmosphere thanks to Hubble's observations. Observations by the James Webb have taught us new things about this cotton candy exoplanet. The data provided by the telescope was analyzed by a team of European astronomers, co-led by researchers from CEA and the Institute of Astronomy at the Belgian University KU Leuven. The scientists were able to detect silicate clouds in Wasp 107b's atmosphere, a first for a planet of this type. According to their analysis, Wasp 107b's atmosphere contains not only clouds of silicate particles, cousins of sand grains, but also molecules of water vapor and sulfur dioxide, SO2. Surprisingly, however, no traces of methane were found. This remains unexplained for the moment, unlike other discoveries such as sulfur dioxide, which have been elucidated by new models. Astrophysicists still don't understand why no trace of methane has been detected in the atmosphere of Wasp 107b, which might force them to revise the models of exoplanet atmospheres known to date. Nevertheless, if the discovery of silicate clouds initially surprised scientists, it can be explained. What astonished astronomers was the presence of these clouds at high altitude. The temperature is only 500 degrees Celsius or 930 degrees Fahrenheit at this altitude, yet the melting temperature of silicate particles tells us that they should form deeper in the atmosphere at higher temperatures. Surprisingly, sand clouds exist and persist at high altitudes. In fact, it would seem that the phenomenon is roughly similar to that of the water cycle on Earth, except that rain is not made up of drops of water but of sand. The droplets of sand rain evaporate into deeper, hotter layers, and the resulting silicate vapor is then carried upwards, where it recondenses to form silicate clouds once again. A discovery that overturns our understanding of exoplanet atmospheres. Wasp 107b appears to be an exotic world, completely different from our own, with complex chemical interactions. There is no equivalent of this exotic world in our solar system, and that's what's so fascinating. Here's another image that may not mean much to you, but represents a real breakthrough for astrophysicists. This image is none other than the discovery by the James Webb Telescope of the most distant black hole ever detected in X-rays. This discovery was made possible by the combination of two space telescopes, the James Webb and Chandra. Because it emits X-rays, we know that it is a supermassive black hole in full growth. The study of this black hole will be invaluable in understanding how some of the first supermassive black holes in our universe were formed. Most astrophysicists agree that there are compact stars at the heart of the vast majority of large galaxies, containing at least 1 million and sometimes several billion solar masses, and behaving as predicted by black hole theory. In other words, supermassive black holes. What we don't know is how these supermassive black holes came to be. There are a number of theories. One of the most widely accepted is that black holes are formed by the accretion of matter from cold filaments. What are cold filaments? They are filaments of cold gas, channeled by filaments of dark matter, which are thought to feed the star-forming matter that makes galaxies grow. Many other hypotheses have been considered. The existence of primordial stars of very high mass, the existence of giant black holes produced during the Big Bang. The discoveries of the James Webb Telescope should enable us to find out more. Let's return to our image. First, Chandra, a space telescope in orbit since 1999, detected a source of X-rays in the UHZ1 galaxy, in the direction of the Able 2744 or Pandora cluster of galaxies, 3.5 billion light-years from the Milky Way. The Pandora cluster, thought to have resulted from the merger of 4 smaller galaxy clusters, is particularly rich in dark matter. This creates a useful gravitational lensing effect for astronomers, making it easier to observe distant galaxies in the visible or near-infrared range. From the data collected by James Webb, researchers were able to establish that galaxy UHZ1 is seen as it was only 470 million years after the Big Bang. As for the Chandra data, they show that the X-ray source associated with this galaxy has all the characteristics of a growing supermassive black hole. This would make it the most distant black hole ever observed in X-rays. What's more, this black hole would have unusual characteristics. With a mass 10 to 100 million times that of the Sun, it contains a quantity of matter equivalent to that of all the stars in the galaxy where it lived in a past revealed to us by photons that traveled more than 13 billion years. We are therefore observing a black hole at an extremely early stage, with a mass similar to that of its host galaxy. According to the researchers, this is a very brief phase in the life of a black hole, during which it weighs about as much as the stars in its galaxy, before falling behind. All these observations confirm the hypothesis that supermassive black holes are the result of a gravitational collapse of a very large gas cloud. Since its launch at the end of 2021, the James Webb Telescope has enabled numerous advances in the fields of cosmology and astrophysics. Not only have new cosmic objects been discovered, but even more knowledge has been gained about the objects already photographed by Hubble, with captivating, colorful images packed with detail. The discoveries made by the James Webb have provided new insights that will not only help us better understand certain cosmic phenomena, but also advance our understanding of the phenomena at the origin of our universe. Here's a first example. In a study published on November 8, 2023, in the journal Astrophysical Journal Letters, a team of researchers explained the role of protoplanetary disks in planet formation, deduced from observations of the James Webb. Protoplanetary disks are agglomerations of gas and dust. They are home to icy rocks, which release water vapors under the effect of extreme temperatures. Protoplanetary disks are therefore predominantly composed of cold water. As they approach newborn stars, icy rocks evaporate, forming rocky planets. This phenomenon was certainly behind the creation of our solar system some 4.6 billion years ago. This hypothesis suggests that even in the most extreme environments of our galaxy, where protoplanetary disks are found, telluric planets like our own could form, which considerably widens the field of possibilities. Here's a second example of a discovery made thanks to the James Webb that has profoundly changed the theories of modern astrophysics. In the vicinity of the Big Dipper constellation, the James Webb Telescope has captured some very old galaxies that, according to our current theories, shouldn't even exist. The 6 galaxies discovered by the James Webb are estimated to have formed only 500 to 7 million years after the Big Bang. They are therefore almost 13 billion years old. However, according to the researchers' calculations, they could contain as many stars as the Milky Way, which doesn't fit our current models. According to currently accepted theories, there must not have been enough matter at that time for galaxies to form as many stars as the Milky Way. These discoveries call into question the very principle of the formation of the first galaxies. At first, because James Webb had already observed very old galaxies, formed around 350 million years after the Big Bang, but they were small and didn't contain as many stars. Galaxies that are both very old and massive, never before seen. It's possible that the red dots observed by the researchers are not very old galaxies, but quasars or supermassive black holes. Or they could be smaller galaxies than scientists have calculated. New data will be needed to confirm the discoveries and find out whether or not we need to revise our current theories and models. New data, that's what we're waiting for to complete all the somewhat disturbing discoveries made over the last 2 years by the telescope. Scientists are keen to make the most of James Webb's potential and use its mission to confirm and refute each of these strange discoveries. Above all, these observations are expected to enable us to reconstruct the history of the universe without any blanks. In fact, the ultimate goal is to fill in all the gaps in our understanding of the universe. How did the universe ignite? How did galaxies come into being? At present, we still don't know how to go back to the first instance of the universe. It's as if we had photos of the universe as a baby, arriving home from the maternity ward, but not of its very first moments. The very first memory we have of the birth of the universe is when it is 378,000 years old. The universe is then what we call the cosmic microwave background. It's made up of tiny specks, representing variations in density. The densest regions become galaxies and stars until they reach us. But how did these tiny specks create galaxies and stars? This period, which lasted several hundred million years when stars didn't yet exist, is known as the Dark Age of the universe. The universe was made up mainly of hydrogen, like a fog in the end, since hydrogen atoms reflect light radiation and we can't see through them. Our knowledge of the history of the universe lacks that moment when the universe emerges from the dark ages and the first stars and galaxies begin to take shape. This is what we'd like to understand with James Webb and future generations of telescopes.